Yeah, good morning my dear students. Today I am going to discuss the rest of the parameters involved in chromatography. So already we discussed some of the mathematical parameters in chromatography. The next important parameter we are going to discuss is plate height. The plate height is also called as HETP. What do you mean by HETP? That is nothing but height equivalent to theoretical plate. So there is a relation between this HETP versus column efficiency. If there is the low value of height equivalent to theoretical plate, automatically the column efficiency will be more. Similarly, if you have number of theoretical plates high, the column efficiency will be better. So both of them are inversely related parameters. So what is this plate height or HETP? So it is a measure of column efficiency which is given by the formula H is equal to sigma square divided by X. What is sigma square? Sigma square is the variance of the band and X is the distance traveled by the sample. So this is the difference, right? So now H is equal to sigma square divided by X. This HETP, as I already told, it is the height equivalent to theoretical plate. So smaller the plate height, you will get the narrow peaks and you will have the better separations. The separations will be much more better. In gas chromatography, the plate height will be equivalent to 0.1 to 1 millimeter. So if you have this lesser plate height for gas chromatography, the column efficiency will be much more better. Whereas in case of HPLC, high performance liquid chromatography, the plate height is equal to around 10 micrometer, right? So this will be much more smaller. For HPLC, the plate height should be very, very less. Then the column efficiency will be much more better, right? The next important parameter is number of theoretical plates, which is given by the terminology N. The number of theoretical plates is the hypothetically observed plates present in the column bands, right? So these number of theoretical plates is given by the formula N is equal to L divided by H. What is called L? L is the length of the column, whereas H is the height equivalent to theoretical plate. So what is the length of the column? Length of the column is nothing but distance. Distance covered by the solute in the column, right? So in other words, if you want to give this thing, already we know H is equal to sigma square by X. So use the same formula here, H is equal to sigma square by X. Therefore, N is equal to L into X divided by sigma square, because it will come in the 1 by H, right? So L into X divided by sigma square you will get as a formula. And L and X, both of them are same. Length of the column and the X is nothing but the distance traveled by the solute in the column. Both of them are same. So we can say that instead of L into X, we can say L square divided by sigma square. So sometimes we can give this with the numerical. So sigma square, basically sigma, if you want to calculate the standard deviation sigma for any peak present in the column, we are using the formula sigma is equal to W by 4, where W is the width of the column, right? So therefore sigma square is equal to W square by 16. So if you put this value here, 16 L square divided by W square. So the number of theoretical plates is equal to 16 L square by W square, right? Which is sometimes equivalent to 16 TR square by W square. Instead of L square, we are using TR, retention time the whole square. Or if you want to use width at half height, W half, if you are using width at half height, then the number will be reduced. That is, instead of 16, N is equal to 5.5 into TR square divided by W half square. So these are all the various formulas just connecting the number of theoretical plates present in the column, which is a hypothetical value. Basically, if the number of theoretical plates is more than 10,000 or 25,000, the column efficiency will be much more better, whether in case of gas chromatography, whether in case of HPLC, right? This is the formula we are using. N is equal to L by H is the formula generally used for calculating the number of theoretical plates in the symmetric peaks. Whereas sometimes if you have the asymmetric peak, right, which is not following the Gaussian distribution, so in asymmetric peak the formula will be little different in calculating the number of theoretical plates. So what is the formula we are using? Suppose this is a peak we are getting, there is an asymmetry, the B portion will be broader and the A portion will be a smaller one, right? So there is a variation, it is not having the symmetry, right? The distance, if you see that, it is not having the uniform symmetry, there is an asymmetry between B and A. And retention time is the center part, that is the TR. Now what we can do that, we are using, and if you look at here, this is the height of the peak. If you look at that, this is 1/10 of the height and this is 9 by 10 of the height of the peak. So what is the formula for calculating the number of theoretical plates for these type of asymmetric peak? N is equal to 41.7 into TR divided by W 0.1 the whole square, the whole divided by A by B plus 1.25. So A value you know very well, this is A, right? This is the peak area A, and B you know very well, this is the B value, right? And what is this W 0.1? TR is the retention time, W 0.1 is nothing but the width at 1/10 height. The width at 1/10 height, that means W 0.1. 1 by 10 is 0.1. The width at 1/10 height we call it as W 0.1. So using this formula we can calculate accurately the number of theoretical plates present in the particular column, especially when the peak is coming as an asymmetric peak, which is not following the Gaussian distribution. Now coming to the next parameter, partition coefficient, already we discussed this partially. So partition coefficient K is equal to Cs divided by Cm, where Cs is the concentration of solute in the stationary phase and Cm is the concentration of solute in the mobile phase, right? Now coming to the plate height equation, there is a very important equation called plate height equation. If we come across this plate height equation, this is also called as Van Demeter equation. The person who discovered this equation called Van Demeter equation. So Van Demeter equation tells us in any chromatography how the column and the flow rate affects the plate height. The plate height should be minimum if you have the better column efficiency. So how the column and the flow rate affects the plate height. This is given by Van Demeter equation, and the equation says that H is equal to A plus B by Ux plus C Ux. What is this terminology H? H is the height equivalent to theoretical plate, and A is nothing but this is basically the A, B, C, all are constants for a given column and stationary phase, and A is a term which is also called as multiple path term or Eddy's diffusion term, whereas B by Ux is basically we call them as longitudinal diffusion term, and Cux, this is basically, C is basically the equilibration time, or simply we can say that mass transfer term, right? So if you look at this diagram, what is this A value? A is the multiple path time. That means when you have, see, whenever you are getting, I told already, diffusion takes place. There is a band broadening taking place whenever you are going, when the sample will be moving through the column, right? So initially it will be having this type of peak, then when it is moving through the column, you will be getting this type of broadening, right? So how this is taking place, mainly if you look at that, the first one is called the multiple path or the Eddy's diffusion term. So here multiple path means the sample or the solute will be traveling inside the column in different paths. In a very multiple path it is going, right? So that is called multiple path term or Eddy's diffusion term, right? Whereas the second one, B by Ux, is called as longitudinal diffusion. What is called longitudinal diffusion? That is this is the longitudinal diffusion, the second one, which is the diffusional broadening along the axis of the column. So how far it will be taking place along the axis of the column, that is called longitudinal diffusion term. We can say that it is spreading in both the directions from the band center along the length of the column, right? Here to here, like that it will go, right? So from the center of the band towards the length of the column it will travel, right? So that is called longitudinal diffusion, and that is very, very important in gas chromatography, because in principles like gas chromatography, the broadening will be, that is diffusion will be more for the gases, because mobile phase is the gas, so the diffusional broadening will be much more, right? So that is a very important factor in gas chromatography. The third important parameter, Cux, is the equilibration time. Equilibration time is nothing but the finite time required for a solute to equilibrate between both the stationary phase and the mobile phase, right? So this is the finite time. There is a time duration taking place for the solute to equilibrate between the stationary phase and the mobile phase in a uniform manner. So the time interval is called equilibration time, which is also called as mass transfer term, right? So generally we call this Ux as the linear flow rate of the mobile phase. We are giving the terminology Ux here and here also. The Ux is referring to the linear flow rate of the mobile phase, right? Now where the impact will be lying, if you look at this, where the impact will be taking place, the impact will be very, very important for this broadening, the diffusion, particularly with related to plate height equation. I am just giving 3 examples here. If you take the packed column, in case of packed column, you will, this multiple path term will be there, longitudinal diffusion also will be there, and then equilibration time, that is your mass transfer term will be there. So all the three will be present. So therefore, if you look at that multiple path term as A and B as longitudinal diffusion, C as mass transfer. So A, B, C is not equal to 0. See, I told already, when the plate height will be equivalent to 0, when the plate height is minimum, automatically the column efficiency will be maximum, right? But in this case of packed column in gas chromatography, the factors like A, B and C is not equal to 0. That means they are higher. So what will happen? The column efficiency will be lesser. Whereas if you take the open tubular column, which is used in gas chromatography, open tubular capillary column, so capillary column size will be very, very less, right? The diameter of the capillary column will be very small. So in this case, what will happen? The A term will be 0. What is A? Multiple path. For example, multiple path means if you have a very small capillary, for example, do you think the solute will be traveling in different multiple path? No, not possible, right? It is not possible because the diameter of the capillary will be very, very small. So the solute will not be traveling here and there and taking the multiple path inside the small capillary tube. Therefore, the A term will be 0. So you can say that the open tubular capillary column will have the better column efficiency as compared to packed column. Now coming to the capillary electrophoresis, if you take the capillary electrophoresis, in case of capillary electrophoresis, again we are using a very small capillary, right? So the A term and the C term is equal to 0. So what is C? C is nothing but equilibration time. In capillary electrophoresis, you are applying the current, electric current, and then you are separating the sample in a very fast manner. So already we are using a small capillary and the sample will be separated by passing the electric current in a fast manner. So what will happen? When you go for this capillary electrophoresis, the mass transfer term will be negligent, right? The mass transfer term will be 0. That means the equilibration time or the finite interval for the sample to equilibrate between the stationary phase and the mobile phase will be very, very less. So we can say the factor A and C term will be equivalent to 0. So therefore we can say the column efficiency will be much more better in case of capillary electrophoresis. Then comes open tubular column and then comes your particular packed column, right? This is all about the things. So we generally call the longitudinal diffusion as the random walk diffusion because you cannot avoid the longitudinal diffusion, particularly in gas chromatography. You cannot avoid that, right? So that B term is an unavoidable term. It is called as random walk diffusion. And if you look at the phases, various phases in chromatography, generally the chromatography based upon the phases, we are classifying them into two types. One is the normal phase chromatography, another one is the reverse phase chromatography. So in reverse phase chromatography, the mobile phase is polar and the stationary phase is non-polar. Whereas the normal phase chromatography, the stationary phase is polar and the mobile phase is non-polar, right? So I can give an example here. In case of stationary phase, polar stationary phase of normal phase chromatography, we are generally using silica gel, particularly in case of HPLC. Whereas in case of reverse phase, the stationary phase used is non-polar. So we are attaching the methyl terminal group along with the silica moiety. So what we are having, we don't have the free selenol groups. We are having this octadecyl silane or octyl silane. So these type of columns we are using as a reverse phase, particularly reverse phase chromatography in HPLC, right? And also in case of gas liquid chromatography, we are using the stationary phase, the polar stationary phase as carbovax, which is basically the polyethylene glycol. And in case of gas liquid chromatography, we are using the non-polar stationary phase. Basically, we are using polydimethyl siloxane. And particularly if you look at that diphenyl X, dimethyl 1-X polysiloxane. Or generally we call them as polydimethyl siloxane, which we are very commonly using as a non-polar stationary phase in gas chromatography, as well as they can be used as an intermediate polar stationary phase also. So this is all about the various mathematical parameters used in chromatography as such. Thank you very much, my dear students. Thank you very much.